Welcome to Chapter 15, where we're going to talk about software interfaces. The quote from today's chapter is from Robert Lee Hotz, and he was a reporter, and in this particular article he wrote for the Los Angeles Times. And this is the story. NASA lost its $125 million Mars climate orbiter because the spacecraft engineers failed to convert English to metric measurements when they were exchanging vital data before the craft was launched. A navigation team at NASA used the metric system of millimeters and meters in its calculations, and the company that designed and built the spacecraft provided the crucial acceleration data in the English system of inches, feet, and pounds. So in a sense, the spacecraft was lost in translation, and this is a highlight of the importance of interfaces with software and hardware and interactions between multiple systems. An interface, software or otherwise, is a boundary across which elements meet and interact, communicate, and coordinate. Elements have interfaces that can control access to their internals, and they can also be subdivided, with each sub-element having its own interface. An element's actors are the other elements, users, or systems with which it interacts. So an actor is something that is causing something to happen. It's acting upon an element. So those actors, like I just said, could be other elements, it could be users, or it could be the systems that the element is interacting with. The collection of the actors with which the element interacts is called the environment for the element. Okay, so you've got the element, you've got the actors, you've got the environment. And then when we say interacts, we mean that anything one element does that can impact the processing of another element. And this interaction is part of the element's interface. It's what that interaction takes place through. Interaction can take a variety of forms, but most of those forms involve the transfer of control or data. In Chapter 1, we defined architecture in terms of elements and their relationships, remember? In this chapter, we're focused on just one type of relationship, and that's the interface relationship. Interfaces are that fundamental abstraction mechanism that we need to connect those elements together. Let's talk about some implied points when we think about interfaces and elements. So first of all, we say that all elements have interfaces. All elements are going to interact with some actor. Otherwise, what's the point? Why bother having an element if it can't interact with anything else? We also imply that interfaces are two-way. When we think about an interface, most of the time we think about what the element does, like what methods does it make available or what does it process. But an element also interacts with its environment by using external resources, or maybe it assumes that the environment behaves in a certain way. And it's important to keep in mind that if those resources are missing, or if the environment doesn't behave the way we expect it to, that element can't function correctly. So an interface is more than what an element provides. It also includes what is required by the element with that environment or the resources. And then the other implied point is that an element can interact with more than one actor through the same interface. For example, if you think about a website being hosted on a web server and multiple clients that are pinging that website at the same time or interacting with that website through the same interface. In this section, we're going to talk about the concepts of multiple interfaces. We're going to talk about resources, operations, properties and events, and the evolution of interfaces. Let's start with multiple interfaces. First, it's possible to split a single interface into multiple interfaces. If we split a single interface into multiple interfaces, each has a related logical purpose, and it serves a different class of actors. So we might have multiple interfaces that provide a separation of concerns. So a specific actor class might require only a subset of the functionality that the single interface has. And so if we split it into multiple interfaces, we can have that subdivision. And that functionality can be provided by just one of those multiple interfaces then. Conversely, the provider of an element might want to grant actors different access rights, like they might want to grant read or write, or they might have a security policy. So by splitting it into multiple interfaces, we can support these different levels of access. For example, if an element wants to expose its functionality through its main interface and give access to debugging or performance monitoring or administrative functions, it can do all of that through separate interfaces. And there could be a public read-only interface for anonymous actors and a private interface that allow the authenticated and authorized actors to modify the state of an element, so they can write to it and change things. Resources. These have syntax and semantics. Resource syntax. The syntax is the resource's signature. It includes any information that another program will need to write a syntactically correct program that uses the resource. So the signature is going to include things like the name of the resource, the names and data types of arguments, if there are any, and on and on. So that's the syntax of a resource. Resource semantics are the result of invoking a resource, and that can come in a variety of forms. It could be the assignment of values to data that the actor invoking the resource might access. For example, the value assignment might be as simple as setting the value of a return argument, or it could be very far-reaching, like updating a central database. It could also be assumptions about the values crossing the interface. It could be changes in the element state brought about by using the resource. It could be events that will be signaled or messages that will be sent as a result of using it. We've got lots of different options. So semantics are the result of invoking a resource. The resources of provided interface consist of operations, events, and properties. These resources are then complemented, they're completed, by an explicit description of the behavior caused or data exchanged when you're accessing each interface resource in terms of its syntax, structure, and semantics. Operations are invoked to transfer control and data to the element for processing. Most operations also return a result. Operations can also fail, and as part of the interface, it should be clear how the actors will detect those errors if there's a failure. So it should either be signaled as part of the output, or there should be some sort of dedicated exception handling channel for those detections. So that's operations. The next part was events. These are normally asynchronous, which means that they don't happen synchronously. Asynchronous, it happens one at a time. One event starts after the completion of the previous event. Synchronous means it's happening at the same time. So events, again, are asynchronous, one at a time, and they can be described in those interfaces. So there's incoming events, which can represent the receipt of a message taken from a queue, or it could be the arrival of a stream element that has to be consumed. Active elements, which are those things that don't passively wait to be invoked, those active elements can produce outgoing events, and those are used to notify listeners or subscribers about interesting things that are happening within the element. So events happen asynchronously and are incoming or outgoing, depending on what they are. Properties. In addition to the data that's transferred by the operation and the event, there's an important aspect of interface, which is the metadata. This could be things like access rights, it could be units of measure, it could be formatting assumptions, and another name for this metadata is properties. As our software evolves, and evolves means it changes, it gets new features, it gets updated with newer technology, there's an evolution that happens with our software, and the interface needs to evolve with it. There's different things we need to keep in mind, but software is encapsulated by that interface, and it's free to evolve without impact on the elements that use the interface as long as the interface itself doesn't change. So the way that those other elements interact with it, as long as that interface doesn't change on the outside, the internals can be updated. Remember, the interface is a contract between the element and its actors. It's handling that relationship, those operations and events. So kind of like a legal contract, you can change those, but you can only change them with certain constraints. And software interfaces should be changed with care and be thoughtful about it. There are 3 different techniques that we're going to go over for how you change your interface for live software. We need to think about our options with deprecation, versioning, and extension. So let's talk about deprecation first. Deprecation means we remove an interface, we take it away. The best practice when you're deprecating is to give lots of notice to the actors of the element. You maybe have worked with code that when you use a dependency, you install a new dependency through import or something like that. If you use something from an older version or even your current version, you might get a warning in the code. It's not an error, but a warning that says that this particular function is deprecated. That, in theory, allows the actors, or you as the developer, time to adjust to that removal before it actually happens. So by putting the warnings in the code or in the log that you're going to see when you interact with it, you can then be proactive about it. Usually, those warnings will link to documentation that lets you know either what to replace that old reference with, so the newer version of it, or what you might need to keep in mind when the deprecation is going to occur if they didn't replace it. So in practice, many actors won't make those updates in advance, but they will discover that deprecation once the interface is removed, and that warning then turns into an error because now it's no longer there. One technique when you're deprecating an interface is to introduce an error code that signifies this interface is going to be deprecated at a specific date, or that it has been deprecated. So we do the best we can to try to communicate deprecation, and that's part of why it's really important to read those error messages and warning messages, because it might have important information that you'll need to keep in mind for when updates happen. Versioning. This is where multiple interfaces can support evolution by keeping the old interface and then also adding a new interface. So the old interface doesn't get changed. We've just added a new one, okay? So the old one can then be deprecated when it's no longer needed or when the decision has been made to no longer support it. And this requires the actor then to specify which version of the interface they want to use. Okay, you might have actually seen this before if you've worked with an API and you've seen v1 or v2 in the endpoints. It might look something like this. As you're hitting an API, this is just an example for an endpoint in the path in a URL, and you can see that it has v1, and they might make a new version and call it v2. So that's one way to keep the old one in place if you're using v1, but then over time, you can start switching over to v2 as you're ready. Extension is our third way to manage evolution. And extending an interface means we leave the original interface unchanged again, and then we add new resources to the interface that embody the desired changes. Let's look at a slide to help explain this one. Okay, so on the left, we have the original interface as it is. And then on the right, if the extension doesn't contain any incompatibilities with the first original interface, then the element can just implement the external interface directly. So you've got just these two interfaces side by side now as multiple interfaces Nothing else has to change. The original interface is still in place. Nothing has been deprecated or changed with that, and we just have additional, an extension of the interface. Now let's look at something a little bit more complicated, where if the extension introduces some incompatibilities, something that doesn't necessarily work with the original interface, then we have to have an internal interface for the element, and then we also need to add a mediator that will help translate between the external interface and the internal interface. So that internal interface is the green color, the mediator is the blue color, our original interface is the orange color, and then our external interface, that is our new extension, is in pink. So an example of this incompatibility, I tried to draw it out to try to show what this looks like. This is just pseudocode, and just to help get the idea across of what we're talking about. So suppose the original interface assumed that apartment numbers were included in an address string. So in the orange box there you see original interface, and it has an argument for address. And that parameter we're going to assume would have the number and the street name. Okay? But the extended interface broke out the apartment numbers as a separate parameter. So extended interface is in the pink, and now you can see we have two arguments, house number and street name. Then the mediator, our blue box, this invokes, if it's invoked from the original interface, then it would parse the address to pull out that apartment number, and then the mediator would pass that apartment number to as a separate parameter into the internal interface. So our green is kind of our new extension. It's our internal interface. We put a new one out there that actors can use, that pink one, and then the mediator will help translate that orange original interface so that it works with our green internal interface. So you can see we have one internal interface, and both of our orange and pink interfaces need to feed into it, but we need to make a slight modification to our original orange interface through the blue to make it go in correctly. So you can see in the blue, all it does is that mediator splits out my address at the space. So we've got a number, space, street name. And then in the original interface, we've edited that just slightly. So it still has the single parameter address, and it takes that address in, and it runs it through the mediator, which splits it out into an array. And now we've got the house number and the street name, which we can then pass into our internal interface. Okay, so that's a very simple and small example, but hopefully that helps you visualize a little bit what a more complicated extension might look like. Now that we've talked about how to evolve our interface, let's look at designing the interface. Decisions about which resources should be externally visible should be driven by the needs of the actors that use those resources. Okay, so actors, remember, are other elements or systems or even users. And adding resources to an interface implies that there is a commitment to maintain those resources as part of the interface for as long as that element will be in use. So if you give me a feature, if you give me a resource, don't take it away from me. Okay? That expectation is that that feature will continue to be there. And once actors start to depend on that resource that you provide through the interface, their elements are going to break if the resource is changed or removed. So the reliability of your architecture is impacted when the interface contract between elements is broken. So it's very important to think about as we're designing interfaces. Other design principles we need to be thinking about. The principle of least surprise. Interfaces should behave consistently with the actor's expectations. Names play a big role here, and giving a resource a good name helps actors have a good hint about what that resource can do. You talk about how for developers, naming is one of the hardest steps, and it's partly because of this. We want to make sure we don't surprise anyone with what to expect, and by giving something a good name, it makes our expectations more clear. We also have the small interfaces principle, And this is where if two elements need to interact, we want them to exchange as little information as possible. Kind of like only know what you have to know. It's a good security policy too. Not having access to more information than you actually need. So small interfaces principle. This is important as we think about our design. The uniform access principle. We want to avoid leaking implementation details through the interface because a resource should be accessible to its actors in the same way, regardless of how it's implemented. The actor doesn't need to know if something has been returned from a cache or if it's been a fresh fetch from some external source, if it's a computation. It shouldn't matter, okay? Uniform access. And then we've got the don't repeat yourself principle, which sounds a lot like dry. Don't repeat yourself, which we talk about with our code. Interfaces should offer a set of composable primitives as opposed to many redundant ways to achieve the same thing. So boil it down to the most basic thing and just reuse that rather than repeating yourself. Consistency is an important part of designing clear interfaces. And as an architect, you should establish and follow the conventions on how resources are named, which we talked about. Naming is really important. How the API parameters are ordered, how errors should be handled, things like that. And developers are going to really appreciate it if the interface follows those same conventions of the underlying platform or the programming language idioms that they're using and that they expect. If you want to continue to win the goodwill of your developers, the other important part is just consistency. Okay, consistency helps minimize the number of development errors based on misunderstanding. If things are consistent, then expectations are a little bit easier to have set because you kind of know what to expect if the same types of patterns are followed. So a successful interaction with an interface requires an agreement on the following things. We have interface scope, interaction style, representation and structure of the exchange data, and error handling. So let's dig into each of those just a little bit more because these are important topics for the design of interfaces. Interface scope. So the scope of an interface defines the collection of resources that are directly available to the actors. You, as the interface designer, you're the software architect, so you're thinking about all of this. You might want to reveal all of the resources, or you might want to constrain access to certain resources or to certain actors. So, for example, you should constrain access for security, for performance management, and for extensibility reasons. You need to think about limiting certain parts for those types of reasons. And a common pattern for constraining and mediating access to those resources an element or a group is establishing a gateway element, which you can see in this picture here. We have our set of actors along the top, and then we have a gateway that then receives all of the events and then spits it out to the different resources. A gateway, which we are going to call the message gateway, will translate actor requests into requests to the target element's resources and then becomes an actor for the target element itself. Okay, so gateways are useful for translating between elements and actors, and it helps give that granularity of the element's resources, which might differ from what an actor needs. Okay, actors may need access to or may be restricted by the different subsets of resources. Remember how we've talked about we could split those things up. And the specifics of the resource, like the number that there are, the protocol, the type, location, properties, that can all change over time. And the gateway can then provide the stable interface. So the actors only need to interact with that gateway, and then that handles everything else. Interaction style. So we need to think about the specifics of designing a particular interface, and this means we need to decide which operations, events, and properties it should feature. And you also need to choose the suitable data representation formats and the data semantics to make sure that the compatibility and the interoperability of your architectural elements work with each other. So remember that opening quote, that gave us an example of these types of decisions. So here's the little bit from that quote again, where we had the English and the metric measurements that didn't get translated properly between the interface. Thinking about that, interfaces are meant to be connected together so that those different elements can communicate, they transfer data, and they can coordinate. They transfer control. So we're transferring data and control, remember. And there's a lot of ways for these kinds of interactions to take place, depending on the mix between communication and coordination, and on whether the elements will be co-located or whether they're remotely deployed. For example, interfaces of co-located elements, things that are with each other, could provide really efficient access to large quantities of data that use the local shared memory buffers. And if elements are expected to be available at the same time, they can use synchronous calls to invoke the operations they need. Or if elements are deployed in an unreliable distributed environment, they're going to need to rely on asynchronous, one after the other, asynchronous interactions based on consuming and producing events. And that's exchanged using the message queues or data streams. So there's a lot of different ways you can have interaction styles. And the two that the book focuses on are RPC and REST. RPC, this is Remote Procedure Call, and this is modeled on procedure calls in imperative languages, except the called procedure is located elsewhere on the network. So the programmer codes the procedure call as if a local procedure were being called with a little bit of syntactic variation, and the call is then translated into a message, which is sent to a remote element where the actual procedure is invoked. And then after that, the results are sent back to the calling element as a message. This method, RPC, dates back from the 1980s, and it's gone through a lot of changes since it was first created. The early versions of this protocol were synchronous, with the parameters of the message being sent as text. And the most recent RPC version, which is called gRPC, transfers parameters in binary and is asynchronous and supports authentication, bidirectional streaming, flow control, blocking, non-blocking bindings, and cancellation and timeouts. Okay, so it's gone through a lot of changes over time, but you can read more about that in the book or online. And then we've also got REST, our representational state transfer. This is a protocol for web services, and it grew out of the original protocol used when the World Wide Web was introduced. REST is made up of 6 constraints that are imposed on the interactions between elements. The first is uniform interface. All of our interactions need to use the same form, which is typically HTTP. The resources on the providing side of the interface are specified using Uniform Resource Identifiers, URIs, and naming conventions should be consistent, and in general, the principle of least surprise, remember our thoughtfulness about naming, should be followed. We want to have consistent expectations. That's our principle of least surprise. We've got the client server. This is where the actors are clients and the resource providers are servers, and they use the client-server pattern that we talked about earlier on. Stateless. All client-server interactions are stateless. The client should not assume that the server has kept any information about the client's last request. It's not keeping track of state at all. And as a result of this, interactions like authorization are encoded into a token, and the token is passed with every single request. So I'll say that again. The resource is not keeping track of the client's last request. So each time the client reaches out to the resource, they need to re-authenticate because it's not keeping that in memory. It's stateless. Cacheable. Caching is applied to the resources when it makes sense. Caching is implemented on the server side or the client side. It can go either way. Tiered system architecture. This is where the server can be broken up into multiple independent elements, and they could also be deployed independently. For example, there could be business logic, and the database could be deployed separate from that business logic. And then our sixth one is code on demand, and this one's optional. This is where the server can provide code to the client that could be executed like JavaScript. Every interface provides the opportunity for us to abstract the internal data representation, which is typically built using programming language data types like objects, arrays, collections, into a different one. That is a representation more suitable for being exchanged across different programming language implementations and then sent across the network. Converting from the internal to the external representation is termed serialization, marshalling, or translation. Let's focus on the selection of general purpose data interchange format, or the representation for sending info over a network. And this decision is based on a few different concerns. First, we need to be thinking about expressiveness. Can the representation serialize arbitrary data structures? Is it optimized for tree objects? Does it need to carry text written in different languages? Think about expressiveness. Interoperability. Does the representation used by the interface match what its actors expect and know how to parse? A standard representation like JSON, which is described just a little bit later in the chapter, that could make it easy for actors to transform the bits that are transmitted across the network into internal data structures. And other thoughts are, does the interface implement a standard? So interoperability, how does it interact with other things? Performance. Does the chosen representation allow efficient usage of available communication bandwidth? What's the algorithmic complexity of parsing representation to read its content into the internal element representation? How much time is spent preparing the messages before they can be sent out? What's the monetary cost of the required bandwidth? This is all the type of stuff you would think about with performance. Implicit coupling. What assumptions do we share between the actors and elements that could lead to errors or data loss when we're decoding messages? Transparency. Is it possible to intercept the exchange messages and observe their content? This is a double-edged sword here. On the one hand, if the self-describing messages help developers more easily debug message payloads, but eavesdroppers can intercept and interpret the content, that's a problem. But on the other hand, binary representations, especially encrypted ones, they require special debugging tools, which is harder for developers to work with as they're figuring things out, but it's much more secure. So we need to think about those different levels of transparency. Like I mentioned when we were talking about interoperability, there are a couple of common programming language independent data representation styles, and they can be divided between textual, like XML or JSON, which is one I had mentioned earlier, or binary, which are protocol buffers. Those are a couple of the different options there are. All right, error handling. Remember at the beginning of the chapter, we talked about how if a resource isn't behaving in the way we expect, or maybe the timing of something is wrong, we need to think about what happens when things don't work the way we expect. So we design for the way things are supposed to be used and how they should work, but we need to also consider what happens when something goes wrong. Some examples of things going wrong. What happens when an operation is called with invalid parameters? What happens when a resource requires more memory than is actually available? What happens when a call to an operation never returns because it failed? What happens when the interface is supposed to trigger a notification event based on the value of a sensor, but the sensor isn't responding or is responding with gibberish? Those are a couple of the things we need to be thinking about. Actors need to know whether the element is working correctly, whether their interaction is successful, and whether an error has occurred. And there's a few different strategies for error handling. We could have failed operations throw an exception. We could have operations return a status indicator with the predefined codes that we've set. These would then need to be tested to detect any wrong outcomes, but that's one way we can handle it. We could use properties to store data. Remember that metadata we talked about with properties, and those could indicate whether the latest operation was successful or not, or whether the stateful elements are in a bad state. We could have error events, like a timeout. That could be triggered for failed asynchronous interactions. Remember, asynchronous is when something happens one after another. It's not happening at the same time, like synchronous. And then one of the last error handling categories is error logs. We could have an error log that could be read by connecting to a specific output data stream. The specification of which exceptions, which status codes, events, information, those different things that are used to describe the erroneous bad outcomes becomes part of the interface of an element. The common sources of errors, which the interface should then handle gracefully. We shouldn't have it just crash and not tell the user what's going on. We should try to handle it so that it's a better experience. We've got a few different sources of errors to be considering. We have incorrect, invalid, or illegal information. For example, calling an operation with a null value parameter when that value should not be null. We could have an element that is in the wrong state for handling the request, where an element might have entered an improper state due to some earlier action, or maybe a lack of a previous action on the part of the same or another actor. For some reason, it's in the wrong state. And what can happen is that maybe it's invoking an operation or reading a property before the element's initialization has completed, and then trying to write to a storage device that has been taken offline by the human operator or something like that. So it's important to have the correct state for the element to do its job in. If you shut down the computer before things finish saving, it can't save. That type of thing. Hardware or software error occurred. That could prevent the element from successfully executing. This could be because of a process failure. It could be a failure of the network to respond. Maybe you got disconnected from the internet. It could be an inability to get more memory, those types of things. And then finally, when an element is not configured correctly, it's just not set up right. For example, you could have a database connection that has that you have a string to set up the connection, and it refers to the wrong server. Maybe it's referring to the dev server and it's in production. So indicating the different sources of the error helps the system to choose the best correction and the best recovery for that type of failure. We could be looking at temporary errors and how we want to deal with them by waiting or retrying. We could think about errors that are because of an invalid input and how we want to require fixing the bad request and resending it. We could have missing dependencies that need to be reinstalled before reattempting. So again, understanding where that source is helps us determine the best way to solve the issue. Documenting the interface. I value documentation so much, but it's one of the hardest things to keep up with software systems because they evolve often very quickly. But we should have a way of documenting the interface. Like I just said, technology evolves quickly, and writing down every single aspect of every possible interaction with a system is just not practical and probably not even desirable for most people. I mean, who wants to read a 300-page book about a software system? So you really should expose only what the actors of an interface need to know in order to interact with it. To put that another way, you choose what information is permissible and appropriate for people to assume about the element. You just tell them what they need to know. The interface documentation indicates what other developers need to know about an interface to use it in combination with other elements. They don't care about any of the extra stuff, just what do they need to know to make it work. Also recognize that different people need to know different information about the interface, and you can separate out sections of the interface documentation for the different stakeholders. So these are the types of people you want to keep in mind as you're writing up some documentation. First, you have the developer of the element, and they need to be aware of the contract, that the interface needs to fulfill, and they can test only the information that's in that interface description. We have the maintainer, who is a special kind of developer who makes the assigned changes to the element and its interface while keeping the disruption to existing actors small. So they're thinking about the versioning or the extension or deprecation. We also have the developer that is making an element that is using that interface. So earlier we said the developer of the element itself. This one is a developer of a different element that uses that interface, and they need to understand the interface's contract and how to use it. You also have the systems integrator and tester. They put the system together from its constituent elements, and they have a strong interest in the behavior of the assembly that they create from it. They are going to need detailed information about all the resources and the functionality that an element can give or requires. An analyst. This role is going to depend on what types of analyses need to be conducted. What do they care about? For performance, they are going to think about the service level agreement, the SLA, what we've guaranteed to our users, so how quickly our response times and things like that. And that way the actors can adjust their requests appropriately to meet those expectations or to be within those expectations. And then we also have the architect, which is looking for assets to reuse in a new system. So you, as an architect, are thinking of work smarter, not harder. You want to take something that is already developed and reuse it in your new system. And this usually starts out by looking at the interfaces of elements from a previous system. You might look in the commercial marketplace to see if there's an off-the-shelf element that can be purchased and do the job for you. And if you are looking at these things, you are looking to see if the element is a candidate for your needs. So as an architect, you're interested in the capabilities of the interface resources, their quality attributes, and any other variability that the element can give you. Whew, that was a really big chapter. There was a lot of information there. Let's just do a quick summary of some of those key points to help reiterate some of the things that we just went through. Architectural elements have interfaces, which are boundaries over which elements interact with each other. Interface design is that architectural duty because you're thinking about the compatible interfaces, allowing architectures that have a lot of elements to do something productive and useful together. You want that relationship of interaction. Elements don't exist on their own without those relationships. A primary use of an interface is to encapsulate that element's implementation so that the implementation can change, the internals can change without impacting the other elements. Elements can have multiple interfaces. They can provide different types of access and privilege to different classes of actors. Interfaces can state which resources the element provide to its actors, what the element needs from its environment to function correctly. And like architectures, interfaces should be as simple as possible, but no simpler. So make sure you meet all the requirements, but don't go beyond that. Interfaces have operations, events, and properties. Those are the parts of the interface that the architect can design. And to do that, you need to decide the element's interface scope, interaction style, representation, structure, and semantics of the exchange data, and error handling. Some of these issues can be addressed by standardized means. For example, data exchange can use mechanisms like XML, JSON, or protocol buffers. We didn't dig too deep into those, but you've probably come across them on your own, especially JSON. That's a very common mechanism to use. All software evolves, including interfaces. Remember that software evolves because that's how you keep users interested. You need to have new features. You need to comply with security updates. You need to keep up with the latest technology. That evolution of software involves the interfaces as well. And there are 3 different techniques that you can use to change your interface using deprecation, where we give a warning out early to let somebody know that this feature or function is going to go away or maybe be replaced by something, and that eventually will turn into an error when that support is dropped. You've got deprecation, that's what we just said. Versioning, where you keep the original version and then you add additional versions, and then the actor will need to refer to which version they want to access. And then we have extension, where we keep the original interface, and then we extend it by adding another interface next to it. And then finally, the interface documentation is going to indicate what other developers need, whatever they need to know about the interface to use it in combination with other elements. How do they make use of it with their own system? And documenting an interface involves deciding which element, operations, events, and properties to expose to the element's actors, and then detailing those out with the interface's syntax and semantics. Thanks for hanging in there for chapter 15, and I will see you at the next chapter.